Classical physics is the study of large-scale objects, such as a ball rolling down an inclined plane, while quantum physics is the study of small particles, such as a single proton or 60 carbon atoms bonded together, which is called a buckyball. Since quantum physics studies small particles which we can't see, smell, or touch, we often use ideas that we learn in classical physics in order to understand quantum physics. However, this leads to many misconceptions in quantum physics, which I'm going to talk about. The first of these misconceptions is that we can never know where a quantum particle is. This misconception comes from the idea of quantum particles having a position, like in classical physics, where position is simply defined by an x, y, and z coordinate in 3D space. However, for a quantum particle, its position is really a probability of finding it at every position in space, where the y-axis is the probability of finding the particle, and the x-axis is just the position in space. This may seem like a trivial distinction to you. However, it is important when we talk about how we think of quantum particles and how they behave. This misunderstanding shows how many people think about quantum particles. It is often thought that all particles have some true position x, y, and z, and it's simply that for quantum particles, when we measure them, we don't find them at one position. We'll find them at spots near their true position, but not exactly on it. However, this isn't true, because in quantum mechanics, particles don't simply exist at one point in space. They have a wave function, often denoted as psi, which gives us the probability of finding them if we were to measure them at certain locations. But they exist at all points in space with a certain probability of measuring them. And it is when we measure them that their wave function changes, called collapsing the wave function, which we'll talk about more in the next section. The second misconception has to do with how observations affect the behavior of quantum particles. In the double slit experiment, we have a wall with two slits, and we send a quantum particle through those two slits. And then we look at the far wall to see where that quantum particle hits. And if we do this many times, and the amplitude is the frequency of where the quantum particle hits, we'll get a curve similar to that one. However, if we were to observe at the first wall which slit that the quantum particle traveled through, in other words, we measure it at that specific location, then we won't get a curve that looks like this. Instead, we'll get simply two peaks depending on which slit the quantum particle goes through. If it goes through this slit, it will end up in this area. If it goes to the bottom slit, it ends in that area. But how can this be? Does the particle somehow know that it's being watched? Or is there something special about a scientist observing a particle? The misconception that there's something special about observing a quantum particle comes from a misunderstanding of the word observation. Because in a quantum physics lab, we can't just look at a quantum particle with our bare eyes because they are on too small a scale for that. See, what an observation or measurement in quantum physics is sending another particle in to collide with the quantum particle, and after the collision, it will carry back information about that particle's position and momentum. This is how simply making observations can change our results, because after this collision, the position and momentum of our particle will be different than before, and thus we'll have different results in our experiment. The last misconception I want to talk about is that when we measure a quantum particle, it could be here or it could be 100 miles away. While this is theoretically true, it is much less likely than people suggest. Even for a particle in a vacuum, the probability of finding it drops off dramatically the farther you get. And in a more realistic situation, where we have particles all over, it is much less likely. This is because all these particles exert forces on one another, and this creates a potential well that the particle has to break out of in order to be found elsewhere. Outside the well, the probability drops exponentially, which is even faster than the case before. In the real-life example of electron tunneling, we typically only find that quantum particles escape only up to distances of 30 angstroms, which is the length of about 30 atoms. And this is way less than finding it 100 miles or 1,000 miles away, which would be unlikely to happen. That concludes this video. I hope you enjoyed it, and thank you for watching. If there's anything you're interested in learning about, or just want to hear my take on something, please leave a comment down below. If you want a more in-depth discussion, please email me at paulfred.learning@gmail.com.